So, hello. Well, good afternoon, everyone. So my name is, well, a quite difficult Greek name. I'm Asteris Apostolis. Thank you very much for being here, and thank you very much for having me. And today I'm going to talk about digital transformation in the aviation maintenance industry and how this is combined with the human challenge, basically, how we can make sure that, let's say, the human capital follows the technical developments. All right, don't waste more time. A bit of an outline. So first of all, I'm going to talk about where we stand right now when it comes to, well, aviation MRO. MRO stands for maintenance, repair, and overhaul, as I guess like most of you know. Discuss a bit the strategies and the timeline of where MRO used to be decades ago and where we stand right now with digitalization. A few later, well, talking a bit about industry and research, because industry has a specific state of the art. Well, research is a bit more advanced, so we're trying to bring industry close to what we do in research and this effort. Well, part of this effort is what we call predictive maintenance, and I will mention specifically predictive maintenance because I think it's a very good use case to describe future challenges and training, and in general, well, training will basically be like a recurrent theme in, well, this whole presentation. And last but not least, talking a bit about what we want to make sure we follow in education to, well, develop professionals that they are up to the standards we will see in the future. All right, very quickly. Well, I'm going to talk about current developments in aviation MRO. What we see is that basically all kinds of technological developments happening right now, meaning that, for example, we have, like, during the last decade or so, we had a very big deployment of composite materials in aviation. And of course, that was like a step change, because somehow we need to, well, maintain and repair those materials, inspect those materials as well, and at the same time, you know, make sure that those repairs or those inspections are somehow automated, because, well, we see that basically with the technological developments we see, like with the introduction of robots or the introduction of artificial intelligence and so on, we move towards like smarter ways to like inspect and maintain like aviation assets. And that's something that, you know, it's a very, well, relevant topic right now. It's a huge discussion about how we move forward with this kind of technologies. That's the first point. But basically, well, while talking about that, let's start discussing a bit, or at least, you know, in my view, where we want to be, let's say in 10, 12 years time, 13 years time in aviation MRO. And the first pillar is smart. And when talking about smart, we mean usually about data-driven technologies, what we, well, call AI in general. It's the use of data, the use of algorithms that they help us to make sure that we maintain assets in a way that, first of all, is efficient, in a way that basically is cost efficient, it's sustainable, and, well, in general, reduces any kind of operational disruption. Because, of course, an asset, well, in maintenance is an asset that cannot like, you know, like produce revenue. Automation, of course, so basically what I just discussed about robots and automated inspection and so on, I think that's like a, well, pretty big chapter as well, and how we can make sure that, well, the people working in aviation are up to date with automation that comes in, well, pretty quickly. Sustainability, and that's something that, first of all, I think it's anyway, well, self-explanatory, that it's important to do, but at the same time, well, we are obliged to follow this kind of road due to any kind of, let's say, government or like European regulations and so on. And last but not least, we see changes in the business side of it. So basically, we see consolidation, we see, you know, things happening in this kind of landscape. So competition as well will change in the coming years. And of course, like whoever does not be up to date with like the technological developments, you know, they might themselves out of business. So it's a pretty complex landscape that, you know, people need to navigate, and that's, you know, an equation that, you know, we're trying to solve basically. All right, well, a quiz time. First of all, that's an engine like that's a G90 basically in a hangar, and well. A question to you, just to, you know, start the discussion, is how many piece parts do you think that an engine like this has, basically? I'm talking about like big blades or like even small like screws and bolts and stuff. Well, who's up for A? Okay, B? and C. Yeah, C is the right answer, basically. It's a very complex asset, and we need to make sure that all those parts work in a proper way in order to have this asset flying. And of course, an engine on the ground does not make any sense. I mean, we need engines to fly. And that's the big challenge, for the coming decades, how make sure that most of the time they fly, the engines are not on the ground on maintenance. All right, so that brings me to my next slide, my next point, basically. Well, very quickly, in the old days, 50, 60, 70 years ago, we were reactive, meaning that, it breaks, we fix it, and we move on. But of course, that's not a very smart strategy, because first of all, it's not that safe. Second, basically, you don't know what to expect, so totally, out of the blue, things might break down, and then you need to fix them, and then, a plane might break on the other side of the world, and then you need to find ways to fix it and bring it back home. So, well, that was too late, basically. If it breaks, it's very late. Well, following, at some point, you said, okay, maybe we should follow another logic and be more reactive, saying, we might follow a specific number of cycles or a specific number of, let's say, flight hours, and then, after a certain point, it's like your car, more or less, after, I don't know, 20,000 kilometers, we need to change your oil or something. So we do that. But that's too early for two reasons. First, because, in fact, we waste material like that. I mean, we throw away, we recycle material that it might be very good to keep flying. And second, I mean, we don't have control on the emission side sometimes. I mean, if we manage to perform maintenance on time, then we have control on, let's say, the efficiency of the different assets, which is translated into emissions as well. So we said, okay, well, we can start using data. And here's, well, where, again, humans need to, well, start changing their mindset about data. We can start using data and make sure that we understand the condition of an asset, and based on this kind of understanding of its condition, we can maintain it just in time. Sometimes it's really just in time, so that doesn't solve the problem of, let's say, being, in the other side of the world, and all of a sudden you have an indication that something's wrong. Then you need to perform maintenance there. So in the end, we say, okay, we need to be predictive, and we need to use data to know in advance where something bad might happen, and then be proactive on that. But of course, not based on cycles or hours, because then we might be too early, but to be predictive, to do maintenance when we need to do maintenance. And this is where we focus right now. Of course, for the future, there's a concept called resilient maintenance, and that comes from SA International, where we don't just perform this maintenance, let's say, in advance, but at the same time, we try to mitigate the effects of this maintenance. So make a connection with the whole system, with flight operations and so on, to make sure that we don't just do maintenance, but we try to prevent all those consequences of making this maintenance in advance. All right, so currently in industry, basically, where we stand. Systems, we have all kinds of systems, but are not designed for large-scale data exploitation, meaning that systems have sensors here and there, and those sensors give some indication of how the system operates. But even with the most, let's say, advanced aircraft and components and systems that were developed, if we take, I don't know, the Dreamliner or the A350 or whatever, those planes were developed 10 years ago, even 15 years ago. And back then, we didn't have the concept yet of predictive maintenance or using data to make sure that we streamline the maintenance of assets. So we have data, but sometimes it's not the right data. So, that's something that, well, we came across many times, yes, let's use those data that we, that keep coming from, let's say, those systems, but then how we use them, it's a bit of a gray area. I mean, we can use them, but they're not optimized, let's say, for a full-scale deployment. Yeah, that's the point I just made. So, well, we do CBM, and that stands for condition-based maintenance, based on monitoring of simple parameters. So basically, engineers, they monitor simple parameters, and they're like, okay, I see that, for example, I don't know, a specific temperature is well, above the red line, or it's approaching the red line, a limit, and then, we react on that. But, that's not, that's sufficient, but of course we can do better. And, well, another thing there is people tend to trust what they do, and that's totally, understandable. But we need to make sure that for the coming generation of professionals, people understand what are the possibilities of data. And I'm talking about people that they develop those systems, but I'm also talking about people that they use those systems. Because, of course, trust is a very important parameter. If you don't trust like a health monitoring, like device or system or like method, then you won't do it, as simple as that, right? I mean, we see lots of examples that, we might have developed a very like smart algorithm, but like if people are not convinced for the usefulness and the accuracy of this algorithm, then, we see this kind of discrepancy between what like a model could do and how people use it. So in the end, even currently, the current, let's say, standard in industry is LLPs, which is life-limited parts. It's like, a part completes 20,000 cycles, we recycle it, independently of its condition. But we can do better, right? So, well, in any case, aircraft produce data. They can be on weak or synthetic data or whatever, but we can use those data, at least to some extent, to predict what we call RUL. That's the remaining useful life of parts, which means that we can use data to understand how much life remains on a specific part. And of course, right now it's not, let's say, a screw or a bolt or whatever, but if we talk about, like big, expensive parts of aircraft systems, yes, we can do better, basically, and predict the remaining useful life. There are many benefits to that, right? So we have fewer disruptions because we can be proactive, we can improve cost efficiency, and we can be more sustainable. And again, sustainability is about, first, like we can use the material and recycle it when we need to recycle it, not earlier than this. But it's about efficiency as well of systems, so it's about emissions too. Like we can optimize emissions this way. But again, well, reality is much more complex than models. So, if we have presence of sand, let's say aircraft operating in the Middle East or sea proximity or whatever, then yeah, things are not as we wish to go. So right now there is a huge research effort to make sure that we can predict things not just in, let's say, optimal conditions, but in conditions that are, like a bit more like challenging. Yeah, well, very quickly, that's the concept of predictive maintenance, and it has like a huge like financial potential. And in fact, well, that's what I just described in a plot. But in general, predictive maintenance, predicts the remaining useful life. That's, I think, the target. And of course, like the target is to, be proactive and predict in advance what we need to do when it comes to maintenance. That's an example, basically, very quickly, like an example again of an engine, and that's like a work we're going to publish next month. But well, this is the deterioration, the real one, and the model, how it's predicted for a high pressure turbine and a low pressure turbine and engine. And models work, basically. So models work indeed. We were pretty accurate in predicting how many cycles these parts have, remain in these parts. But again, we see two challenges. First challenge is that, if I take this plot and show it to an engineer, they're going to be, yeah, that that looks right. But first of all, I'm not, am I supposed to trust this kind of system? Yeah, maybe not, right? And second is if I'm taking this this plot and go to a regulator, because by the way, aviation is very much regulated, they're going to tell me, nice try, but we have no framework to certify this kind of prediction. So there is an effort right now, first of all, to make this kind of methods certifiable with regulators like the EASA in Europe and the FAA in the US and some other smaller local regulators. And the second thing is that we need again to build trust with the engineers. And in my experience, basically, because this kind of methods require a multidisciplinary approach, right? I've seen this kind of predictions being made by data scientists. Nothing against data scientists, but it's the same people that make this kind of suggestions on if you shop on Amazon and you shop, I don't know, a remote control, then they will tell you, well, if you buy this, you might need to buy a mouse. But of course, if you make this kind of wrong prediction and instead of a mouse, they, suggest, I don't know, printing paper, nothing will be heard. But if we talk about planes, we need to trust predictions. We need to make sure that there is engineering input as well, not just data science input, but engineering input. Yeah, sure. Okay, yeah, well, no worries. All right. So, data challenge, and I think that's very much related to people as well and human. That comes from a consultancy company, but it's a pretty good report, basically. And we see that when we design stuff, so that's like the engineering part, we are very much digitalized. So we use lots of data and lots of, let's say, computer science to make sure that we design things like the best possible way. Same more or less applies to manufacturing, right? It's very much digitalized. But when we start like operating or servicing or retiring stuff, like decommissioning stuff, then digitalization is not like, like a strong point. And there are good reasons for that. Again, it's about trust. It's about like the conservative nature of aviation, because safety is above all, so we cannot really make steps that we're not ready to do. But then again, if we want to like take advantage of the opportunities we see, we need to make sure that we are much more digitalized. And of course, that does not apply only, like to people that design those systems, but it applies also to the mechanics and the technicians on the shop floor, because they need to understand why they do things the way they do them. It applies to the people that design these kind of things. And of course, last but not least, it's very important, we need to make sure that the executive management is also educated in this kind of, let's say, landscape. Because of course, executive management, they are the people that they initiate these kind of things. They need to support those things. They need to understand how those things work. And I'm not talking, of course, about the mathematical details of algorithms, but they need to be aware of what's possible, what is the current status, have a pretty good understanding of the landscape they're dealing with. So, well, like a list of current developments. We hear lots of things about digital twins, right? But, well, I can tell you, like, I've seen methods that were developed decades ago for simulation being rebranded as digital twins. So sometimes we need to be a bit cautious what a digital twin is. Well, there are some very good examples as well of digital twins, but, we have the tendency to name everything a digital twin these days. So we need to read a bit behind, like, the lines and make sure that, that's something with substance and that's something that, companies can use at their benefit. Of course, well, we're talking about technologies, we need to make sure that are well integrated to what we have so far, and they can be operated in different kinds of systems. Data models, methods, and algorithms, like a huge part, and again, people need to be data savvy to make sure that those kind of, let's say, methods are well accepted within organizations. And us, by the way, as educational institutions, we need to make sure that we include these kind of things in our curriculum, and we do these days. Well, an example here is that, well, we have two tracks, students that study aviation engineering and students studying aviation management. And they have a minor like that they do for 6 months during their third year. And a vast majority of students, they go for data science these days because they understand the potential of these kind of things. So as educators, we need to be up to date with that. Again, explainable predictions, very, very important. I mean, well, people need to understand how a prediction is being made. If an algorithm says to someone, you need to change this kind of part in, well, like 3 times flight or something like that, people need to understand why, because otherwise they won't follow what an algorithm says. They need to understand why is that. It doesn't have to be a black box. And then they can take the right decision. Of course, legislation certification needs to be, let's say, aligned with what I just described. And then again, lots of efforts are being made in this front. So, well, in the end, it's about upskilling the workforce. And that will happen, yeah, that can happen basically at school, can happen at a company, and so on. So in the end, we need to have professionals, basically, that have, let's say, a broad understanding of different disciplines and competencies and so on. But they need to also specialize in specific streams. So they need to be aware of what's happening out there with data and stuff and algorithms and all of that, but they need to also be specialized in their own work. And that's a pretty famous T-shape that came originally from IBM, and you can find this in lots of, let's say, presentations and books. Well, almost finished. So basically, as we discussed before, we have this Bright Sky Mobility Fund, and it's an effort with all those stakeholders to basically develop some new technologies. About smart MRO, that's inspections and repairs. About smart availability, and that's mainly related to predictive maintenance. Smart autonomous airside, autonomous vehicles on the airport side. Smart access, that's about security, and I think that's pretty relevant with what's happening at Schiphol these days. And smart training. And that's about the use of virtual reality and augmented reality for the mechanics at the shop floor. And by the way, we see that in this kind of scheme, we have a collaboration of MBOs, HBOs, such as HFA, and also universities, such as TU Delft. So basically, we try to make sure that every different level of education is up to date with this kind of developments. So I'm going to finish with a question to you. So let's say you board the plane, and they tell you, you know, well, this plane, no one inspected anything, it's about algorithms. So basically, there is no inspection, but everything is fine because an algorithm inspected everything, and we're sure that it's fine. Will you board this plane or not?
Who wants to give a reaction?
Well, this is it working? Yes, working.
Yeah.
Thank you for your interesting talk about how it's working in aerospace.
Yeah.
This is exactly what my question was about just
Right.
a second ago. Can you go to slide 10 with the algorithms?
Yes.
So today we're talking about people who have to make decisions based on these algorithms.
Yeah.
And at time 1, I think,
Yes.
4, 5 out of 6 algorithms say it's almost broken.
Yeah. Time 1. Yeah.
Yeah, so it's so the
Yeah, it's about,
predicted
like-
it's the very first line. It's
Yeah. So
very close to 0. So the first one upper left is okay, but all the other
here. Yes.
ones are very
Yeah.
very low.
Yeah. A comment on that.
What would you say about it?
Yeah.
And also to the people who have to use this.
Yeah,
Yeah.
that's true. That's true. We're not there yet, and this is why, you know, if we trust the algorithm completely, you know, the algorithm might say, you know, this is going to break. So, you know, human needs to be part of the loop anyway, and human need to have a look and say, you know, this doesn't seem right to me. I need to make sure that, you know, well, I use my engineering opinion to make sure that in the end, you know, like I don't take decisions that are not the right ones. So yes, in the end, I'm not sure if we're gonna ever see like assets being completely, you know, monitored by machines without human intervention. But we need to make sure that, let's say, humans are trained enough to understand what does this mean and why the algorithm takes this kind of decision. Because if we see that, you know, this decision is wrong, we might go into like the specifics of the algorithm and say, you know, that's why, and that's how we can fix it. Of course, not everyone can do it, but at least, you know, we need to make sure that someone will do it.
Yeah. Yeah, or just say there's
Yeah.
a small calibration period in the start and don't have a look at it
Yeah.
and don't pay too much attention. But
Well,
once it has
Yeah.
sort of
Yeah.
move
In any case,
towards,
towards the end, you see
yeah.
that, you know, the predictions are much more accurate.
yeah, exactly.
Other questions, please.
Who has another question? There aren't any questions from the people from home and the office. Well, they can still put it in the chat, and then we'll ask you. But thank you for this interesting presentation. Aviation is always a business way ahead of a lot of people represent other businesses here.
Yeah.
So do you have a learning or an advice from the aviation business for other sectors who are represented here?
Well, you know, planes are complex, but essentially they're machines, right? I mean, and well, any kind of machine can break, like from, let's say, a huge aircraft engine to like a pump that pumps some kind of like liquid, like in a, you know, like air conditioning system or whatever. So, well, in my opinion, we're going to see this kind of technologies, of course, not to the full extent of technologies, but this kind of technologies, once they are mature enough, you know, I expect them to, you know, like be part of other industries too. So yeah, my view is that, you know, like we need to make sure that, and we do it, that people are educated about what's happening and what's going on in the field of, let's say, data science in general. Again, we don't expect everyone to be a data scientist, but at least, you know, to be aware of the possibilities, because then, you know, people, you know, like managers from all kinds of industries might see opportunities there, because there are like, you know, different kinds of opportunities that we see in other industries. And by the way, that's a very good point, because, well, at school where I work, we have this kind of collaboration with other departments as well, so with engineering or with like maritime and so on, and we make sure that we're aligned, and we make sure as well that we are all working towards, well, same kind of goal. So we have, like, say, working groups inside the school where we talk about this kind of technologies, and we make sure that we learn from each other.
Okay, great.
Yep.
These crossovers. Thank you very much.
Thanks a lot.
Oh.
Yeah, sure.
Lex?
there are a few OEMs, Boeing, Airbus, and Embraer. And then you have a lot of first tier and second tier suppliers. And what you see nowadays is that they are all doing their development regarding the production of new sustainable airplanes.
Yeah.
And in 2035 we have new sustainable airplanes. And what we are doing with maintenance, because will we have kerosene? Will we have hybrid power strains? Will we have hydrogens? Which from this part, the thinking about the maintenance consequences during this phase that they are developing.
That's a very good point. A couple of weeks ago, I was in a meeting with a program called Clean Aviation, and that's a joint undertake from the European Union and some other, let's say, partners, where they develop the research towards this kind of technologies. So they discussed about new planes, as you said, the new shapes and new fuels and so on. And then at some point, I raised my hand and I asked, what about maintenance? What about, like operating this kind of assets? Because, we can design assets, but then we found ourselves, like, as an industry, as operators, as airlines, sometimes that, like the OEMs, they make all kinds of nice plans, and then when it comes to, the everyday use of assets, there are lots of problems. So they were like, yeah, we know, clean aviation is about, like, designing stuff. Yeah, maintenance will come later. Well, I don't agree with that, to be honest with you. We need to make sure that this kind of maintainability is included from the very beginning. Otherwise, we might be too late. So right now, in fact, as school as well, and me personally, I'm involved in all kinds of different initiatives about starting, like, the design, thinking about maintenance for electric planes, for hydrogen planes, and so on. Or not, let's say, well, fully on, but we take into consideration this kind of new technologies and trying to, well, do some first steps on how maintenance of those assets will look like when the time comes. So yes, you're absolutely right that we need to make sure that we don't expect till 2035 and the planes start being operated, and then we're like, yeah, we didn't think about maintenance. And something like that, not to that extent, happened with the introduction of composite materials. Like they're light, they're very efficient, in operating them. But if there is some kind of, let's say, issue with the material, like some kind of crack or whatever, then things are much more complex compared to, let's say, well, relative, like conventional aluminum or whatever alloys. So we need to make sure that we are on board this train, and we do our best to be there. Yeah, sure.
Thanks very much.
Thanks.
We have to stop right now for the next speaker, but a warm applause for Asteris.
Thank you.